Yeah.
Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Bao Truong and Thiem Hoang with us today. Hello, Bao. Hello, Thiem.
Yeah. Yeah. Hello, friends. Yeah, and nice to see you in the AAS Channel Series. Channel Series.
Hi, Frank.
Hello,
Yeah,
sir.
thank you for having me.
Well, thank you both for agreeing to talk about your very awesome article, which we will get to very shortly. And Bao, let's start with you. What's your geolocation? Where are you at?
Well, currently I'm in Daejeon, South Korea. The weather is a little bit nice today, so yeah.
Woo. Spring is coming. Spring is coming.
Yeah, spring is coming, and yeah, I don't know why last 2 days they have snow, but now the weather is become more warmer.
Ah,
So we will see a cherry blossom in some day.
very good. Very good. So it is March 19th of 2025 as we record this, and I'm in Phoenix, and we definitely don't get any snow. We are in the
Oh,
desert. No, it's good. And Bao, what's your position there?
well, technically, so I'm both master and PhD student, and I stay in Korea for about like 2 years for my master, and also currently I'm in the PhD phase, so I'm a first year PhD student.
Very cool. Very cool. I'm going to predict a very awesome PhD thesis. How about that?
Yeah.
Very good. And Thiem, you are also in Korea, yes?
Yeah. Currently, I'm working at Korea Astronomy and Space Science Institute in Daejeon.
Very cool. And you're a professor there?
Yeah, I'm the principal researcher, but at the same time, I am also full professor at the Korea University of Science and Technology.
Very cool. Very nice. Um, and Thiem, what do you like to do for research?
Well, my research, so I'm very interested in the whole universe. Basically, I'm very curious about how matter in the interstellar medium, like a gas and dust,
Hmm.
undergo the gravitational collapse to form new stars,
Yes.
planets, and even the origin of life.
Okay.
So I
Cool.
try to understand the origin of stars, planets, and life from the point of view of dust.
Very cool. Very cool. And Bao, in your young trajectory here as a PhD student, what do you like to do research on?
Yes. So, in fact, my interest is about magnetic field in both the interstellar medium and also in star forming region. But the question is like we measure the magnetic field. Usually, we measure in the plane of the sky or in the line of sight. So we only have like one preferred direction. So my question is like how we can measure that in the three-dimensional space. So
Right.
that's why I am interested. Is like how we can measure the magnetic field in 3D magnetic field in 3D space, and at the same time, we can combine that between measure the 3D magnetic field and also dust property using both dust polarization. That's also what we are going to discuss in this paper that we present today.
Cool. And that is going to bring us to this very awesome article.
Yeah.
And let me do screen share and boom. This is the APJ. It is open access. It's the open access era, people. You can go get a copy for free. Go get one. Probing 3D magnetic fields using starlight polarization and grain alignment theory. And Bao and Thiem, take us away.
Okay, so let's me go first. Yeah, so the main motivation for this paper is how we can extract three-dimensional magnetic fields using starlight polarization and grain alignment theory. Um, so first, starlight polarization, that means the polarization of distant starlight, which was discovered in 1949 by two independent American scientists in 1949.
Mhm.
And soon after the discovery of starlight polarization, uh, people recognized that dust grains in the interstellar medium must be non-spherical, and
Yep.
somehow they must align systematically with a large-scale um, field in order to induce polarization. And then the large-scale field here is attributed to the large-scale magnetic fields. So the discovery of starlight evolution actually now resulted in two new phenomena. One is the um, existence of magnetic fields, and the alignment of dust grains in the interstellar medium.
I'm with
So, yeah. So the polarization of starlight actually carries very unique information, not only about magnetic fields, but also about the dust properties,
yes.
including the alignment. Yeah. And so in this paper, we try to get the maximum information from starlight polarization.
Yes.
We focus on 3D magnetic fields, and based on what we know about grain alignment, that is grain alignment theory.
Yes.
Yeah, so in order to do that, we have to now develop the model for starlight polarization.
Okay.
And if you can go down to the figure one, I can explain
Sure.
a little.
Slide on down, and we will get some illustration of grain alignment. Okay.
Yeah, so the starlight polarization results from the alignment of dust grains. So here in this figure one, we illustrate one specific dust grains which is elongated, and it is spinning along the angular momentum J here.
Okay. Okay.
And the background star is a yellow star here, and then we observe the distant starlight going along the Z direction.
Yes, line of sight. Okay, I'm with
Yeah,
you. Hmm.
yeah. So the magnetic field is now described by the B naught, the blue arrow.
Yes.
But in the plan of the sky,
Yeah.
we have two components. X and Y is the plan of the sky. We have a BOS is the plan of the sky, and B along the line of sight.
Yes.
So the polarization of starlight is now caused by the difference in the extinction of starlight by the dust grains. So, for example, the extinction of starlight along the y-axis is more than along the short axis.
Yeah.
So the starlight that we observe now is polarized with the polarization vector along the long axis of dust grain.
Okay, cool.
That first is about the polarization direction, and in terms of the polarization degree, it depends on the grain properties, like how elongation the grain is, and
Yeah.
also the uh, inclination angle of magnetic field, gamma.
Yes.
And one more parameter is the how alignment of dust grain with magnetic field. I mean, alignment is here is between J and B.
Yes.
So there are three key parameters that involves in the polarization of star. First, the magnetic field inclination angle.
Yes.
Second, grain shape.
Yes.
And third is the alignment degree.
I'm with you.
Yeah. So if we can predict the alignment degree, and if we can um, constrain the grain shape, and
Okay.
then we can infer the inclination angle of magnetic field using the data that we observe for starlight polarization. And so that is the key idea.
Cool. Very good. I'm with you. Okay. Yep.
And yeah, that is the basic concept. But because we are scientists, so we need to develop the quantitative model.
Yeah.
So the mathematical model. Yeah, so the mathematical model you can go down to the method. Yeah, so equation that equation 4.
Yes. We're still in uniform magnetic field. Okay. One,
Yeah,
two.
yeah, equation.
Polarization degree. In case it's small, then we get
Yeah, so we go step by step. So
Mhm.
first we develop the model for starlight polarization, assuming that magnetic field is uniform along the line of sight.
Uh-huh.
So that means it doesn't have any tangling. So the magnetic field can be described by a straight line, making some angle with the line of sight.
Yes.
And with that, now we can model the polarization by equation 5. So that is the degree of polarization of starlight. So
Okay.
in this equation, you can see several parameters. So first is NH is a total amount of hydrogen along the left side.
Yes.
And psi square gamma, it characterizes the inclination angle of magnetic field.
Mm-hmm.
And the F align is the alignment degree of dust grains for a given size A. And
Yeah. Mm-hmm.
And CPO is actually the intrinsic polarization cross section. So it is dependent on the grain shape. And ND is a dust number density. Yeah,
Yes.
so you see that from equation 5 now we can predict the polarization level of starlight.
Mm-hmm. And you
Yeah,
did this in your first paper here, just to bring that up.
yeah.
Paper one. Yeah. Okay.
So now we need to test this model first. So using the synthetic observation, just to make sure that whether this simplified model can accurately describe the real observation data.
Okay. Okay. Mm-hmm. Mm-hmm.
Okay, so can you go now to the equation?
Which one would you like?
I think I can go to equation 30.
13,
Uh, oh no, 27.
27. Okay. So basically we're doing the integrals here, doing an approximation. Then we come down to the grain alignment functions, and we come down to equation
27. Yeah.
27. Ah, here we go, sine squared. Mm-hmm.
Yeah. Because now so we can predict the polarization of starlight. Sorry. Uh, so the ingression angle now can be inferred
Mm-hmm.
using the observed polarization and the portion that we can predict. So in the numerator, that is the observed polarization, and the denominator is a theoretical prediction for the polarization.
Okay. What is F turb?
Yeah, F term here, as I mentioned, initially we developed the model for uniform magnetic field,
Yes. Ah, turbulence.
but in fact, along the line of sight, magnetic field has a turbulence, tangling.
Yes.
So we introduce one parameter that characterize the effect of magnetic field tangling on the polarization.
Okay.
So in the case of uniform magnetic field, F term is 1. That means it doesn't cause any effect on polarization.
Yep.
But in fact, the F term is less than 1. That means the magnetic field fluctuation can reduce the net polarization degree.
Okay, cool. I'm with
Yeah.
you. Mm-hmm.
And
Good.
then now from equation 27, we can infer the ingression angle. That
Yes.
is a simple case first. Yeah, so see this basically the theory. And we have to test the theory before we apply the technique to the real observation.
Yes. It's always a good thing to do.
Uh, yeah, and so we have a test using the MHD simulation. It's very interesting that recently we developed some uh, numerical code that can allow us to perform synthetic observation of polarization, and that we used to test this method. So now Bao, he can take over and describe about the numerical work.
Okay, I will jump on. All right. So, okay, so following about as team discussed, so in order to measure the inclination angle, we need to have bothly the dust properties such as the grain shape and also the grain size distribution.
Yes.
Secondly, the realignment degree.
Yeah.
Third one is the magnetic field fluctuation. And if we combine it together and combine that with the observational data, and then we can finally get the inclination angle. However, in the real observation, so both gas, dust, and magnetic field is changing along left side. So we need to know how our new technique can be applied to the real observation. So in this case, we're using our synthetic observation that we can generate from the MHD simulation to test that how we can infer the inclination angle from the starlight polarization efficiency. So in this case, so I using the MHD simulation that was produced by Tomoshi, MHD simulation produced by Tomoshi and Hennenpel in 18. So this is the MHD simulation for formation of the filamentary cloud with filamentary cloud. And from that MHD simulation, so we put that into our updated Polarization course. So this is the radiative transfer course that we can generate the radiative transfer of the polarization based on our. And in this course, so my colleague Nguyễn Châu Giang, so she also including the modern alignment theory in this course. So which means that we both know about the alignment and we input into the main code. And finally, we can generate about the synthetic observation of the polarization. And from that synthetic observation, so we will test our new technique to see if we can infer the inclination angle from the synthetic polarization.
Right. You know that answer. Okay.
Yeah.
Okay. I'm with you. We're good.
Okay, so I think you can scroll up to figure 6.
Figure 6, and I lost.
Yeah, figure 6 about.
Okay.
Yeah, about polarization coefficient fraction. Okay, so firstly from the synthetic modeling, so we will know about the alignment degree. So on the alignment degree, but one thing I want to warn is that for the starlight polarization, it's really sensitive to the wavelength, both optical and near infrared wavelength.
Sure.
So that's why when we measure about the polarization degree, we need to take care about the wavelength measurement. So on the left is in the V band in about 0.55 micrometer, that is in the optical band.
Yep.
And on the right panel is in the near infrared band, it's about 2.2 micrometer.
Yep.
And here I show about the polarization coefficient fraction. This describes about the alignment efficiency of the grain with respect to the gas column density from the outer cloud to the inner cloud, as you can see that in both two figures. And on the top is correspond to the visual extinction. So one you can see that in the outer cloud where the gas density is low, so the alignment is more efficient. So that's why you can see that there is the flattens out. Yeah, there's a flat profile in the F-bowl, and toward to the denser cloud in the inner region. So due to the gas dynamization at the higher density, so you can see that there is the gray alignment. So the loss of the alignment is become more efficient. And that's why you can see that the F-bowl in here, it decreases with increasing of the gas column density. With F-bowl, it corresponds to the square to the power of minus 0.1 in this case. And not only just testing about the variation of the alignment efficiency from the outer the inner region. We also including in different model of grain magnetic properties. So in this case, I show about four model that we consider in terms of the grain alignment model. So first one is the ideal RAS, which means that if for all of the grain larger than the alignment size, so they can be aligned with the magnetic field. But this is just the ideal situation. But in fact, the universe is not really ideal. And in fact, the alignment decrease, it also depends on the grain magnetic property. So here on the three model, and you can see that in the green, blue, and purple line. So there are three models based on different grain magnetic property. So for PM in here is the parametric grain, which means grain have the iron inside, and that iron randomly distribute inside the grain. So that is the parametric grain. So the blue and the purple one is the supermagnetic grain, SVM. So supermagnetic grain means that the iron, there is not randomly distributed, but they will combine it together to form like the iron cluster, And as they form that iron cluster, so they will acting like the larger magnetic moment, and that helps the grain to be more aligned with the magnetic field. That is the
Right.
that is for the supermatic grain. And also I vary the number of iron cluster from 50 to about 1000. So you can see that the apple that I show in both the left and the right panel in here. So if if the grammatic property is supermatic and have the higher number of iron inclusion, so the level of apple will be increasing entirely in our measurement.
Okay.
Yeah.
Let's see. So all of the faint dots are from the 3D simulation. So there's a cloud of dots for each color, right? And so the cloud is the distribution, the one sigma.
Yeah.
Okay.
Yeah, so in this case, so I just doing like I just take all of the cloud and then calculate the running mean from the outer to the inner region of the cloud and
Okay.
get the relation between the F pole and also the gas column density.
Right. Okay.
A-
Very nice.
And one of the key measures I want to emphasize in here is that the gray alignment loss is really efficient in the denser region. So in this case, it's really denser in the higher AV, about like up to about AV larger than A. So which means that when we measure the inclination angle, we should in the denser region, like in the filament or in the Starlight core, we should take care of the grain alignment loss in order to have the proper result about the inclination angle. That's also the key message that I want to tell in here.
Cool. Okay. Good. Very good.
Yeah,
And
so I would like to mention a little bit about the history of tracing 3D magnetic fields using starlight polarization and gas polarization. So before our work, there are some papers by Chen et al. And Hu and Nazarian.
Yes.
They
Yes.
use
Yes.
yeah,
Yes.
their papers are also published in APJ.
Yes, I know.
Yeah, but in their approach, they assume that the alignment is uniform across the molecular cloud. So that correspond to the constant F pole. The polarization fraction is constant.
Yes.
But the difference from our work is we use a grain alignment theory. So
Yeah.
you can see clearly that the
It's not flat.
polarization, it's not flat. It decreases rapidly in denser region.
Yeah.
So our technique accounts accurately for the decrease in polarization efficiency, and
Cool.
that affects a lot the inference of ingression angle.
Oh yeah, certainly. Yeah, very good. Cool. Okay. Great.
yeah, okay.
Great plot.
Yeah, so we see like this, so that we see that from the figure 6, so there is the importance of the gray alignment in the way that we think, in the way we're thinking about how we can infer about inclination angle. I think like we can go to the figure 7.
Okay.
Yeah.
Slide down a little bit. We got figure 7. Okay, here we go. Variation of the intrinsic polarization efficiency. Yes. Okay, here we go. Yep.
Okay, so for the figure 7, so as we know about the gray alignment, so now we can input that into the Polaris course that we've previously developed, and then we can generate about the synthetic data of the polarization. So on the left is the intrinsic polarization. So in this case, so intrinsic polarization is mean we consider very perfect case. That is the magnetic field. There's no magnetic field tangling. The magnetic field is uniform, and the gray alignment is perfect for all the potential sides. So in this case, so for the intrinsic polarization, it's only depend on the intrinsic dust property, such as the grain shape and also grain size distribution. So one we can say that for intrinsic polarization, so in the outer cloud, so the polarization fraction, the polarization efficiency is become flat for all of the observed wavelength. However, toward to the inner region, it's also depend on the different observed wavelength. So here's the thing. So when the polarized optical depth is become much larger than 1, which means that the environment is optically thick to the polarized starlight. So it will causing the polarization degree is become saturated, which means it will reach to 1, and that's causing the decrease of the polarization efficiency when we
Nice.
write in different observed wavelength. So for the case, so for instance, from B band to R band, that is in optical wavelength. So at that optical wavelength, so the starlight cannot passing through the inner dense region. So that's why you could see that the crop is will going into the lower extinction region,
Lower
like
extinction.
it well, like
Right.
yeah,
Yep.
it's about 10. But if we're using the near infrared wavelength, so the starlight, the polarized starlight, is become transparent to the cloud,
Yes.
and the effect of the polarized extinction effect is will happen to in the more inner dense region of
Right.
the cloud, like up to about like 30 to 40, up to about visual extinction to 30 to 40. So this is the key. So this is really important in the way that we can how we can trace the three-dimensional field using different observed wavelength. That is
Right.
that is what we know about the intrinsic polarization. So
Right.
on the left one is the case when we including the realignment theory. So on the right one, when you read the realignment theory and also the realistic model, the realistic morphology of the magnetic field from the filamentary cloud. So you can see that for all of the wavelength, so due to the effect of the realignment, so in the outer cloud, so since the realignment is more efficient, so you can say that there is the nearly the flat profile, but toward to the inner region. So because of the loss of the realignment, so you can see that for all of the wavelength, you will see like there's the polarization loss toward to the inner region.
Correct.
Up to about, yeah. So
Wow.
that is the, yeah.
Wow. Okay. Very cool.
And
With you. Yeah. Okay.
and after we know about the intrinsic and also the polarization efficiency, when we're including the realignment, we want to test how our physical model can describe well the synthetic observation, which means like how our physical model can match with the synthetic observation generated by the polaris. So you may turn to the figure A. Yeah.
Figure 8. So we go down one. Ooh.
Okay, so figure A is the comparison between so on the horizontal axis is the price and efficiency that we can calculate from our physical model.
Analytic.
Yeah, analytical. And on the vertical axis is the synthetic price and efficiency that we generate from the polaris. And on the left is in the case where we consider there's no turbulence, there's no realignment.
Yes.
For our physical model. And on the right is when we include the realignment and also magnetic fluctuation. And you could see that surprisingly. So by including the realignment and magnetic field fluctuation, we can our physical model describe well with the synthetic observation, which means that our physical model is ready to be used to infer the inclination angle from the synthetic observation. That is
Very
the
cool.
testing in the figure A.
Very cool. Very nice plot.
Okay, and so now we have all the ingredients together. We have the alignment degree, the F-ball that I showed you previously. We have the intrinsic polarization that describe about intrinsic dust properties such as the grain shape and also the grain size distribution. We also have the and also combine that with the synthetic polarization that we generate from the polaris. And finally, we can inferring again about the inclination angle. So I think you may go through to figure 9.
Drum roll.
Afterward, yeah.
Drum roll. And whammo, here we go. Inferring angles. Very cool.
Yeah, okay, so now we have all the ingredients, and now we can start to inferring the inclination angle. Okay, so on the left is the inclination angle that we infer from the polarization efficiency, but polarization efficiency that we measure in the optical band, that is in the V band, and on the right is when we measure in the near infrared band. So there's a so when we tracing the inclination angle, so both of the band they can trace well the inclination angle. However, there's the key difference, and you can see that they have some white pixel in here.
Right.
You can see that.
Right.
Yeah. So that white pixel is the non-pixel. So that non-pixel is mean like when we're tracing the inclination angle, we can return the value that is psi square is go over than 1.
Correct. I'm with
Which
you.
means we cannot trace the inclination angle at that region. And the reason that we cannot trace inclination angle is strongly depend on the observed wavelength. So okay, so in the optical band, so as I explained earlier, so the polarized starlight cannot passing through to the higher denser region. So you can say that there's really many non-value in the denser region, and in the optical band, so you can trace the three-dimensional field only up to about the region is with smaller AV smaller than 3. That is in the optical band. So here I shows the black contour in here is the
Gotcha.
region
That's
where
the
the
black
AV, yeah, it's the black contour.
Uh-huh.
So
And blue
if
is
we're using the near-infrared band, so the story will be go further, because for near-infrared band, the polarized starlight can passing through to the inner dense region.
yes.
And that means that we can trace the three-dimensional field not only in the outer cloud, but also in the inner cloud up
Deeper.
to the AV to about 30. And that I represent here in the blue contour.
Yep.
So which means like in which region that we can trace three-dimensional inclination angle using polarization efficiency for different wavelengths. So that is the wavelength dependence in this case.
That's so cool.
Yeah. So yeah, that's it about the figure. Now about the possibility that we can use our new technique to infer the inclination angle using the synthetic polarization efficiency. So I might think like you may go to the figure 11.
Okay.
Yeah.
Zoom out a little bit. 9, 10, and there's the last equation. What was that, figure 11? Yes?
Yeah, figure 11. Okay. So figure 11 is the way that so after we have the inclination angle from the synthetic polarization efficiency, we need to compare that if our result is comparable to the inclination angle that we can get from the MHD simulation.
Yes.
So on the left one is the value, is the histogram of the inclination angle. So for the dashed color line here is the case when we don't have including the realignment mode. We don't have including the realignment degree or any kind of the magnetic turbulence. And the solid color line is when we including the realignment degree and also the magnetic turbulence in our physical model to infer about inclination angle. And the black one in here is the inclination angle that we can get from the MHD simulation.
Yep.
And one you can say that there's really key difference. So if by including the realignment and also magnetic turbulence, so we can infer the inclination angle, which is close to the inclination angle that we can get from MHD simulation. So which means that this is raised the importance to including the realignment and magnetic turbulence when we calculate about the inclination angle.
Absolutely. Very cool.
Yeah, and on the right is the
really big effect too.
yeah, and on the right is the deviation between the inclination angle that we derive from our new technique and the inclination angle that we can get from the MHD simulation. So you can see that our new technique, when we including the realignment and magnetic turbulence, so we can get the inclination angle close to the MHD simulation by the deviation is only about 2 to 6 degrees. That is one of the main improvement.
That's nice. Very nice. Yeah. Yep. Beautiful.
Yeah. Okay, so the previous story the previous figure that I showed you is when we consider the ideal case of the relative torque alignment theory. That is all of the grain larger than alignment side that can be aligned with the magnetic field. But when we analyze about the grain alignment degree, as I told before in the figure of the apple, we also need to consider about grain magnetic properties, the parametric grain and subparametric grain with different level of error inclusion.
Okay.
So
Okay.
in figure, I think in figure, okay, let's see. All right, okay. So I think it's in figure 12. Yeah, I think we should move to figure 12.
This is a variation of P sin over NH. Yeah.
Yeah, okay. So in figure 12, so here we're not only just using the ideal rad, we also varying the grain magnetic property for parametric grain to subparametric grain with the increasing level of resolution.
Yep.
And what we can say that by by including, so we can see that for supermatic grain, they have the higher polarization efficiency due to the higher alignment degree, and that causing the higher for the entire cloud for
Right.
both observation from V band to K band.
Order of
So this affect a lot. So then by including the dramatic properties, so we can also inferring the inclination angle really well. So I might think
Yeah.
that you may need to go to figure 16.
Okay, very cool. I get that one. Figure 16, 13, 14, 14, 15, and let's go to 16. Zoom in
Yeah,
a
okay.
bit here. Okay.
Okay, so 16 in here is the histogram. Histogram showed the difference between the inclination angle that we can infer from our technique for different brain alignment model
Yes.
comparison to the inclination angle when we get from the MPD simulation. So one, we can see that by including the gray alignment, gray magnetic property for the gray alignment, so we can also
Okay.
inferring the inclination angle and also close to the MPD result of the MPD simulation in this case.
Okay, cool. I got you. Let me soak this in a bit. 0,
Yeah.
3, 60, 90. Okay. Okay.
Yeah, and not just that, we also vary with different viewing angle. So here in the reverse figure, I show the case when the viewing angle between the magnetic field and the light upside is about 90 degrees. But when we changing the view, in this figure, we prove that for different viewing angles. So our new technique by consider both the gray alignment and also magnetic turbulence, so we can also prove the English. We can prove the inclination angle really well and close to the result from MPD simulation.
Yeah. Very.
So as it raised the importance of the gray alignment in the way that we can trace the proper inclination angle using the dust polarization efficiency. That is the key message from the figure 16.
Yeah, regardless of the viewing angle.
Yeah.
Yeah.
I think I would like to add a little bit.
Okay.
So here for different models, we consider that iron atoms are like distributed inside dust grains.
Yes.
In the form of iron clusters.
Yes.
But because we don't know what is the size of iron cluster, so we have to play a little bit. So we assume that, okay, the iron cluster may be very small, but it may grow to bigger one.
Yes.
So the iron cluster size is characterized by the parameter n cluster here.
Yes, NCL.
But of course, the size of iron cluster here are small, so that grains are still supermagnetic. So they are not like a metallic iron. Okay.
Right. It's not like it's not like a needle. Okay.
And also the assumption that iron cluster are present inside dust grains is very well justified because from observation we know that most of iron is depleted from the gas. So
yes.
Iron must be in the form of solid material.
Yep.
So that assumption is really natural.
Yeah, that's very reasonable. Yes. Thank you.
Okay, and so far as I presented on the figure, so we're using for just one of the grades. So one of the key things that I want to emphasize in here is that the polarized starlight is really sensitive to wavelength, and not only sensitive to the wavelength, it's also sensitive to the grain size distribution, especially for the maximum grain size of the environment can be achieved due to the grain role. So
Right.
that's why we should. So that's why when we use this new technique, we also need to constrain the intrinsic dust property. The maximum grain size and the grain shape should be really correct in order to get the true inclination angle that is comparable to an MHD simulation.
Okay.
So on the I think on figure. Okay, so on figure 19, I think we go to the figure 19.
Slide down a little bit. 18 and 19, grain growth.
Yeah, grain growth. Okay. So previously I showed the result when we consider the maximum grain size about 0.25 micrometer. So how about when we vary the maximum grain size from 0.25 to 0.1? So you can see, so in this figure, so I show about polarization coefficient fraction when we measure at optical and near-infrared wavelength.
Yes.
And you could see that due to the rentral, the gray alignment can be more efficient into the inner region. And
Oh,
so you can see that the transition between the region of star to alignment loss start to shift to the inner region.
yes.
And this feature is more prominent when we observe that in the near-infrared wavelength due to for larger range they are start to be more polarized in the longer wavelength
Yeah.
at near-infrared wavelength. So that's why you can see that this feature is more prominent in the near-infrared band. So that's why there's the wavelength dependent, not the wavelength dependent with respect to the grain size also. That's why we should take into account when we're doing the when we want to trace the inclination angle using the Poisson efficiency.
Well, you're going to get all kinds of information out of this. Okay, good. Good. I'm with you. All right.
Okay, so by including the French row, so I may think like you go to the figure 22.
22. Let's bang out
Okay.
figure 20, 21, and 22. Let's see if we can pull it up a little bit.
Yeah.
Yeah.
Okay, the figure 22 is one of the key measures is that by consider the French row like the increase like the proper A max for different environment. So we can get the inclination angle as the same as the ideal rad case that I showed earlier. So which means that when we constrain about it, so here on the top is in the case when we constrain inclination angle in the optical band, and on the bottom panel is when we constrain in the near-infrared band. So you can see that. So for different panel from the I think from the left, the middle, and the right is the increasing in the maximum frame size. So you can see that if we properly constrain the maximum frame size in the environment, the result is all of the same between this figure in both optical and also in infrared band, which means this is raise the importance of constraining intrinsic dust property in order to properly trace the inclination angle of the magnetic field.
Very cool. Very
Yeah.
nice. Yeah.
So now we see like in order to trace the inclination angle, we need to better constrain about the intrinsic dust property. We need to better constrain about ray alignment degree. And also we better constrain to about the magnetic turbulence. That is the key message that we given throughout this paper. Yeah.
Right. But with
Yeah, I think for intrinsic dust properties, we can use a work from Bruce Rain and Brandon Hensley.
yes.
So in the paper, they constrain the grain shape using Starlight operation as well. So our idea, okay, if a grain shape can be constrained using Starlight operation in the diffuse medium, and then for grain shape we mean the grain elongation or axial ratio, and then we assume that during the process of star formation, the grain size can increase, but the grain elongation may be slightly changed.
Okay.
And in that assumption, now we can consider the grain elongation to be fixed, and then we take that as an intrinsic dust property.
Yeah.
So we can go forward with using grain alignment theory and observation data to infer the magnetic field inclination angle.
That's so nice.
Yeah, but of course, we cannot rule out the possibility that even grain shape can also change from the diffuse to Oleger clouds and to star forming region.
Okay.
So that is one possibility, but we cannot rule out.
Yeah, because then you're mixing this. Okay. Very nice.
Yeah, and now we are testing really well with the synthetic observation when we varying about the alignment degree, where we have varying about the grammatic properties, and also we varying about the intrinsic dust properties, such as the maximum frame size. So how can we apply in the real observation? So we'll jump to the discussion in section 5.2. in this case.
Oop, 5.2. I went the wrong way.
Yeah,
One
this will
sec.
go far. This will go a little bit far. Okay.
1 and
Yeah.
5. I'll get there. Sorry. 5.1 and 5.2. How did I lose that?
Okay, so the
Here we go.
the the 5.2 in here is how we can trace the 3D magnetic field in star-forming region when we're using the starlight polarization efficiency. So as I showed in the previous figure, in figure A, so there is the dependence when we're using the inclination, when we trace the inclination angle for different wavelength. So in optical band, we can only trace in the low extinction region with AV smaller than 3. So this is really essential when we want to trace the 3D magnetic field in the diffuse medium or in the molecular cloud with the AV is much smaller than 3.
Right.
But for near infrared, we can trace further to the inner dense region with the AV with the transition AV can be go up to about 30. So this is really important in order we want to trace the 3D magnetic field in the denser region, such as in the filament and in the dense core using the near-infrared polarization efficiency. But of course, like when we trace to this region, we should take into account the loss of the realignment due to the gas ionization at higher density.
Yes.
That is the key when we want to apply the new
Got
technique for different wavelength and for different region in star-forming region.
Yeah, because they're not just sitting there. Okay, good, cool.
And also one thing that I want to mention in here is that we also can use the new technique in order to make the tomography of the 3D magnetic field along the left side, just what the Yeshua do when he combined the starlight polarization with the Gaia data. So I might think that you may go to the section 5.4.
I'm with you. 5.4 and yep, 3D tomography.
So okay, so one of the main advantage between the starlight polarization and the thermal dust polarization that we usually measure by using Planck and JCMT and Soviet Hawk Plus is that we know the information of the spectral star distance. So as we know about the spectral star distance, so we may know like in which region along the left side that causing the starlight polarization in the plane of the sky. And recently that we have many data from the Gaia data release 2, data release 3, and I think that later on we will release 4 and 5 for the for more accuracy of the measurement of the stellar distance. So we can utilize the combination between the Gaia and the starlight polarization to study about how the magnetic field can be varying along different cloud components along a left side.
Yes.
But in that technique, so we only can have the 2D tomography. So combine that with our new technique when we have the information about the realignment, we also can do that tomography, but in 3D.
Right.
And that is the way we can understand further about how the impact of the 3D magnetic field in the formation in the diffuse
clouds. Yeah.
Yeah. So it's our new technique can make a further improvement about the current work from Yesodoi and other experts working in starlight polarization used when they combine it with the Gaia data.
Cool. We'll come to this moment. Okay.
And the final thing I want to mention is that so in order to measure the 3D magnetic field, we need to understand well about the dust property. And as I mentioned, like by constraining the intrinsic dust properties, such as the grain shape and also the maximum grain size, so we can trace well the 3D magnetic field. And vice versa, if we know well about the 3D magnetic field, we can use that to the dust polarization, and then we can trace back to constraining about the intrinsic dust property. So the key message is that the constraint between the dust property and the 3D magnetic field within the dust polarization degree is associated to each other.
Yes.
We know one thing and we can know the other. We can know the other thing. That's one of the key messages. So in the section 5.5, so we're pointing out that if we know the 3D magnetic field by using other techniques such as combine between the dust polarization and polarization that Manus Tahani do in her paper in in 2018, 2020. We can use another technique like the Starlight operation and the velocity gradient technique that is by Yeho and Alex Lazarian. So if we know about the 3D magnetic field in this technique, so we can use that 3D information in order to constrain again about the intrinsic dust property. So which means that these one are associated to each other when we're doing the dust property. This is the open potential of constraining both the 3D magnetic field and also dust property when we're using the dust polarization. That is the key message I want to emphasize in this section.
Very cool. Good. Good. Okay. Anything else you want to cover?
I think one more thing is Bao. He's now, and also another student of me, they are now using this technique for the real observation data by Sophie Hawk Plus and also JCMT.
Good.
And also Starlight operation. So
Good.
we try to apply the technique to the real data. And hopefully it will become a useful tool for people to plot 3D magnetic fields as well as dust physics using polarization applied.
Very good.
So I would like to emphasize that the polarization applied is very important for, but usually people use the polarization to only study magnetic fields or study dust. So we here we are trying to explore the polarization to study both magnetic fields and dust properties. So that is only doable when we have a well-established theory of grain alignment.
Yes.
And the grain alignment is, of course, a very long-standing question. How does grains get aligned with magnetic field?
Yep.
And after about 70 years now, we understand a little bit or like reasonably well about the alignment process and also the efficiency of grain alignment. So that's why it can driving us to work on this project.
Cool. Beautiful. Beautiful work. Beautiful work. Very nice.
Thank you.
And Thiem, I want to thank you so much for walking us through your very lovely APJ article. Very nice.
Yeah, thank you very much, Frank.
Yeah, thank you, my friends.
Yeah, and you you mentioned it a couple of times. So let me just push on it a little bit. And where do you think we go in the near-ish future on this topic? You mentioned, okay, now we're going to actually apply it to real observed data. So that would be thing. Is there other things that could be done theoretically? Is there stuff that could be done in the lab to measure grain alignments as a function of B or something like that? So just sort of next steps. Where do you think we go from here, given the published article?
Okay, so that is a very good question. And actually, so far as I understand, there's no any laboratory studies on grain alignment.
Okay.
But the process of grain alignment now, we understand, it requires grain to spin very fast. So spin very fast so that they are not randomized by the collision with the gas. And the second is the spinning grains become aligned with magnetic field. So if we want to test the alignment mechanism, we can test first the spin up of dust grains, for example, by radiative torques, and then the alignment process of spinning grains with magnetic field. For the first process, the spin up of dust grains by radiative torques, it has been already tested in 2004 by NASA, by some people in NASA. But the second process is the alignment between the spinning grains and magnetic field.
Yes.
It has not been studied in the lab. So I think that is one open question that would require testing. Because when we develop the theory for grain alignment, we consider the interstellar medium condition, and the time scale for grain alignment is like 100,000 years or so.
Well, that's not happening in a lab.
Right.
But you can maybe make scaling arguments, right? To scale.
Oh yeah, right.
Yeah.
So for example, we can use very strong magnetic fields
She'll crank it up.
The gas and also the radiation are much stronger, so we can perform the scaling experiment.
Yeah, very cool.
Okay, so I may add some of my point of view in terms of the observation. Okay, so throughout the paper, so we can see like if we can constrain the intrinsic dust property really well, we can trade the inclination angle of the magnetic field, and that's it. We got that information in 3D. But that is really also, but that strategy is also really challenged in observation because even in the intrinsic dust property itself, it's also changing within the environment. So we know that there's the range from the diffuse medium to the denser region.
Right.
So which means that it will causing the changing, the increasing, not only just about the grain size, but it's also increasing about the grain shape. It's the elongation of the grain is become more elongated when we go to the denser region. So that is the challenging when we want to do in the real observation. We need to constrain really well the intrinsic dust polarization at different environment in order to get information about the 3D magnetic field. So that is the one of my point of view is like how we can thinking about how we can do both. We can do constrain both the 3D magnetic field and the dust property at once in just one dust polarization decrease. So that is what I'm thinking right now. Is like we can use some kind of the deep learning model, machine learning model, in order to do if we have the observational data for the polarization degree in the thermal dust polarization or the polarization efficiency in the starlight polarization, we go into the deep learning model and then we can constrain two property, 3D magnetic field and the intrinsic property at once. So that is also the advanced thing, and also that is the current project that we are currently established and working on right now to accelerate more about how we know about the 3D magnetic field and the dust property just in one single dust polarization degree.
Yeah, that'll be really awesome to see this develop over the next couple of years. Very cool.
Yeah.
All right, Bao, Thiem, thank you so much once again.
And thank you very much.
Yeah,
it's
thank you so
a
much.
pleasure talking to you.
Thank you.
Yeah, it's really a pleasure talking with you.
Good night.
Good night.
And that will do, everyone. And I hope this made your grain astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Okay, bye-bye.
Yeah, goodbye.